Hi, and welcome to the Unit 3.2 Atomic Structure video. Before we get started, um, make sure you take the Unit 3 diagnostic, which has a weight of 0. You can find the Unit 3 diagnostic and a blank bubble sheet in the orange folders on your desk. When you're done with the diagnostic, put your bubble sheet inside the diagnostic and then drop it off in the folders in the table on the back. Okay. After taking the diagnostic, then you can watch the video and you can take notes on the Unit 3.2 video note sheet that's also in the orange folder. This will be collected for participation points, so make sure you fill that out. And then after the videos, there's notes for you to take in your notebook. So these will be separate notes. These are handwritten notes that go in your notebook, and these notes can be found in Google Classroom. Okay, so if you've taken the diagnostic, go ahead and grab this note page, which is again in the orange folder on your desk, and then we can get started. If you haven't taken the diagnostic, pause this video now and get started on the diagnostic. All right, in the 3.1 video, we learned about periodic trends, and we said that one of the reasons why periodic trends are important is because they help us to predict and explain properties of matter. For example, oil is not soluble in water, but sugar is. So how could we determine that from the chemical formula? So if you start with a chemical formula, you can use that information to show how the atoms will be connected, and then from there that gives you the structure, and then from the structure you can see if it's going to be soluble or insoluble. Now this may seem like a long process, but the basis of that process is understanding periodic trends. So we looked at these periodic trends, quantitative and qualitative trends. Before we dive into the lesson, let's sort of review what we know about periodic trends. So on your note packet, what you're going to do is you're going to label the periodic table with periodic trends. What does that mean? Anytime you label a table with periodic trends, you have to draw some arrows, one heading to the left and one heading down. And along these arrows, you're going to show what happens to the atomic number, atomic radius, and electronegativity. Do they increase or decrease? In addition to the quantitative trends that are shown here, you're also going to do qualitative trends, which are the ones that point towards the corners there. So you're going to draw these arrows pointing towards the fluorine corner, and then that one pointing towards cesium or francium. And then you're going to write along here the qualitative trends, metallic versus non-metallic, reactivity, whether they increase or decrease. So you're going to pause the video now, and then when you press play again, we'll see what these trends are. Great. So at this moment, you should have trends that look somewhat like this. And so far, all we've done is we've defined what these trends are, and we've sort of just started memorizing what the trends are. But we haven't gone beyond that. And that's not enough because it's kind of hard to memorize a bunch of information. It's better to understand why. And in order to understand these periodic trends, we need to understand the structure of the atom. Now, I know you guys know a lot about atoms already, and I know that because when we did our previous KWL, you guys were saying some things about atoms and in terms of the what do we know section. So what I want us to do is I want us to take a moment to capture what we know in this preview. Now, there are two reasons why previewing your knowledge is important. One is important because it helps you become more confident as you're learning things, because then you'll recognize, hey, I actually did know that. And you've already stated that to yourself and to others. The other reason why it's important is because it helps to surface any misconceptions that you may have. So you may think something about an atom that's not exactly quite true. By writing it down now, when you learn what the truth is, then you're able to say, oh, I used to think this, and now I know that this is not true. Okay, and that will help you then to better learn and better understand and not get so stuck. So I'm going to ask you to preview what you know about atoms in two ways. First, I want you to draw a picture of what you think an atom looks like. You can rely on things that you've previously seen an atom to look like, or you can just make up what you think it looks like. And then I want you to list all the things you know about an atom. So that can be terms, structures, what it's made of, how it's used, etc. Anything that you think you know about an atom, you can go ahead and capture it. So take a couple minutes to do this preview. Please don't look anything up for the preview. Do it on your own because that is how we'll capture our knowledge. Great. So I can't wait to see what you've done in your preview. And I'll look forward to seeing that when I collect your papers. All right, so let's now talk about what an atom is. And these are probably things that you've heard of before. An atom is known as the smallest unit of matter that retains the properties of matter. And that fancy definition may be a little confusing. So maybe a better way of thinking about it is if you had a gold bar and you took that gold bar and you cut it in half. And then you cut the halves in halves and you kept cutting it in half and you kept cutting it in half until you couldn't cut it anymore. What you have left is an atom of gold. And what makes that an atom of gold is that if you cut that atom of gold in half, it's no longer gold anymore. So if you want to keep cutting it in half and it still be gold, the smallest thing you can get to is an atom. And that's what it means. It's the smallest unit of matter that retains the properties of matter. It's still gold when it's an atom. Okay, so we know atoms are really tiny and they're really small and all these things like that. They're too small for us to see. So what does an atom look like? Well, we do have tools called electron microscopes that can help us get a better sense of what an atom looks like, but these actually aren't quite accurate. We still don't know what an atom looks like. The electron microscopes don't show us the parts of an atom, etc. So we still don't know what an atom looks like. However, we can use models to sort of help us understand what an atom looks like. And models are essentially sort of drawings that help us describe the structure of atoms. And it's important to note that the models of atoms have sort of evolved over the years. Here's the first one, the Greek model, which just shows atoms as sort of really tiny marbles. The Thomson's plum pudding model, in which he showed sort of like positive and negative parts floating around in space. The next model was the Rutherford model, and this model came up through a very famous experiment called the Guilfoyle experiment. And in this experiment, he determined that the nucleus is sort of like at the center of the atom is this nucleus, which is this dense, compact space, which has all this positive charge, and around it are these negative charges floating in space. And then there was the Bohr model, where neutrons were discovered, and you have the protons and neutrons now in the nucleus, and electrons are orbiting around, sort of the way planets orbit around a sun. They're orbiting around, electrons orbit around the nucleus. And then the cloud model, which sort of shows you where that electrons are moving really, really, really fast. So you can't see them, and you can't tell exactly where they are. However, you can, through this cloud, determine where they're most likely to be, and the darker the shading of the cloud, that means that you're most likely to find more likely to find an electron there. And so all of these models have been important to helping us understand atoms. The Thomson and Rutherford model, however, are not very accurate. They did help us to identify that there are positive and negative parts of an atom and where they could be. But we don't use those anymore. We still use the Greek model because they're really helpful in particle diagrams, just a really simple description of an atom. And we still use the cloud model because it's more accurate in terms of understanding that electrons move fast, and we can't predict, we can't see exactly where they are, but we can predict where they are. But in order to understand the periodic trends in the periodic table, what we're going to use is what's known as the Bohr model. So this is the most helpful model for understanding periodic trends. But before we get into the Bohr model, let's take a moment to think about the basics of the atom. So the atoms are made of three things. Those three things are protons, neutrons, and electrons. And they're located in different places. Where are protons and neutrons located? That's right, inside the nucleus. And electrons will be on the outside of the nucleus. The next thing we should know about these parts of the atom, they're called subatomic particles, are their relative masses. So protons and neutrons are much bigger than electrons, and we can measure their size in terms of their mass. So we say protons and neutrons weigh approximately 1 atomic mass unit, or 1 AMU. AMU is a unit of mass, just like grams or pounds, but it's a unit of mass for something really, really, really tiny. So they're approximately 1 AMU, but the electron's approximately 0 because it's so tiny. Even though it's not quite 0, it's almost 0. So we say approximately 0. Charges. Some of the particles have charges. So what are the charges of protons, neutrons, and electrons? That's right, you probably know protons are positive, neutrons are 0, and electrons are negative. The good thing about knowing that protons and neutrons and electrons, what their charges are, can sort of help us figure out the charge of an atom or ion. Okay, so now that we've talked about the subatomic particles and sort of those pieces of information, there are still some other basics of the atom we should know. First off, the proton is equivalent to the atomic number found in the periodic table, and you probably remember that from before. The other thing that's super important is that the proton is what we use to identify an element. That is to say that all carbon atoms and only carbon atoms have 6 protons. So if you see an atom with 6 protons, you know it's carbon. However, if you see an atom with 8 neutrons, you don't know that that's carbon. That can be anything. If you see an atom with 6 electrons, you don't know that that's carbon. That can be anything. So when it comes down to identifying an element, we have to use the protons. And that's because the number of neutrons and electrons can vary, and the atom is still the atom. So carbon can have 8 neutrons, 6 neutrons, 5 neutrons, and it's still carbon as long as it has 6 protons. The other thing to know is that the protons equals the number of neutrons if the atom is neutral, meaning it does not have a charge. And that's because the positive and negative charges will cancel each other out, and so the overall charge is 0. However, if the atom has a charge, meaning it's an ion, then the protons don't equal the number of neutrons. And you can sort of figure out what the charge is or how many protons and neutrons you have from this information. These are basics we'll get more into later, but now let's go into the Bohr model. So for the Bohr model, the protons and neutrons are shown in the nucleus at the center of the atom, and the electrons sort of orbit around it, revolve around the neutrons in shells. And you can sort of think of that as like if you cut an onion open, the rings that you see, those will be like the shells. And in the very center will be the nucleus. Now, in this model of the Bohr, the neutrons and protons are shown as separate pieces, but that's oftentimes hard to draw. So what we're going to start doing for our nucleus, instead of doing it that way, we're just going to draw a circle and then write the number of protons, so 6p, and number of neutrons, 8n. And that makes it easier, but the rest of it we'll still do. We'll still draw the shells and electrons in the shell. All right, so how exactly do we draw a Bohr model? Let's take something like carbon, which is shown here. The first thing we're going to do is we're going to draw the nucleus. And in the nucleus, we need to put the number of protons and neutrons. So remember, the number of protons is the atomic number, and that's going to be 6, because that's what we see in the periodic table. The neutrons, on the other hand, because it will vary, I will give that to you. So I can give it to you in different ways, but for right now, I'm just going to just tell you what it is, but I will give you the number of neutrons. So with that being said, we can draw our nucleus with 6p, 8n. The next thing is we're going to draw the shells where the electrons are. Now, to draw the number of shells, you could figure it out from the number of electrons you have, but that oftentimes is a lot of work. A really simple trick is that the number of shells you need to draw is equal to the period that the element is in the periodic table. So let's look at carbon. Periods are rows, remember, and carbon is in the second row. So if we count the number of rows in the second row, that means it's in the second period. So since it's in the second period, I'm going to draw 2 shells, and I drew those in this blue color. Now we're going to fill in our electrons, and the electrons, couple things to know. The number of electrons, if it's neutral, is going to equal the number of protons. So first we need to know the number of electrons. Since it's neutral, which most of the time I will tell you that it's neutral, we're going to have 6 electrons. The other thing to know is that we got to fill the electrons in from the inner shell, the one closest to the nucleus first, then to the outer shell. So inner to outer. And that the inner shell can only fit 2. So we have a total of 6 electrons. That means they all can't go in that first shell closest to the nucleus. So we can only put a maximum of 2 there, and we're going to put those 2 next to each other. Since we used 2 of our 6, we've got 4 more. Those 4 are going to go in the outer shell. 1, 2, 3, 4. And I do corner to corner before I start doubling them up. All right, so that is our Bohr model. That's how we draw a Bohr model. Okay, so now take a moment. I want you to, in your packet, what have you learned about atoms and what questions do you have? Remember, I'm going to collect this for participation point next class. So make sure you get this done and then keep this and return it to me next class. Finally, after you've done your reflection, don't forget to take notes in your notebook. The notes can be found in Google Classroom. That's it for this video. I hope you've surfaced things that you've previously known, and maybe there's some new things that came up for you. And that's it. Have a quality day.